So I hope everyone can see the screen. So thank you very much, Andrew, for the introduction. So I have the pleasure of holding the energy simulation chair for fractured and geothermal carbonate reservoirs. And just would like to take the opportunity to thank Energy Simulation and its board for having the trust in renewing the chair program earlier this year. Previously, we were the energy simulation chair for carbonate reservoirs, and we have transitioned as part of energy simulation mission away from the classical oil and gas work that we have done to use our long-standing expertise in modeling naturally fractured reservoirs and tackle a much wider range of challenges related to low-carbon geoenergy systems, such as geothermal reservoirs, but also looking at things like CO2 leakage through fractures, or possibly even hydrogen storage and how hydrogen migrates through fractures in reservoirs. We have three key research themes within the chair program. The first one is, this is what I'm talking about today, how we can do some really fast static dynamic modeling for geological reservoirs, fractured geological reservoirs, to get some very quick feedback of how geological uncertainties could impact reservoir properties, reservoir dynamics. Another theme where we do quite some detailed work on characterizing flow behaviors across scales. It includes some more recent work on machine learning, but also multi-scale imaging, X-ray CT imaging, synchrotron imaging. And then there's always a drive that we try to test all the technologies, all the workflows, all the concepts that we develop at the end of the day in some real field applications. And I have the honor of being part of the United Downs Deep Geothermal project, which is the largest the deepest onshore well that has ever been drilled in the UK. It's located in Cornwall. We're doing some fracture modeling for this geothermal reservoir there in partnerships with colleagues from British Geological Survey, the Lyell Centre, Edinburgh, and other universities. So without further ado, I think that quote, if you can't draw it, don't model it. I think I've heard it first from Mike King at Texas A&M, who I believe attributes it to Glenn Williams at BP. And this quote really motivates what the Rapid Reservoir Modeling project is all about. We try to draw geological concepts very quickly to create prototypes of reservoir models and immediately get dynamic feedback. And I want to point out that this project wouldn't exist without energy simulation, because the idea was born out of discussions I had very early on when I became a chair with Mario Costa Souza from University of Calgary, who was chair, energy simulation chair at that time. It's a collaborative effort between Mario Costa Souza's group at the University of Calgary and Matt Jackson and his group at Imperial College London. And the project has been live and has been making progress for the last 7 years, and it has been funded by the companies that you see here at the bottom. So what are we trying to do in this RRM, the Rapid Reservoir Modeling project? We are aware that efficient management of geoenergy reservoirs, so that could be a geothermal reservoir, it could be a reservoir for carbon capture and storage, for hydrogen storage, for oil and gas. We need good reservoir models, but the current workflows that we have, they have a number of persistent ongoing challenges. One is we have very slow turnaround times. It takes a lot of time from the characterization to ending up with our dynamic models, the very linear workflows. So this means that any geological concepts are locked in early in the process. It's difficult, perhaps even impossible to explore very quickly how different geological concepts, different engineering concepts could impact reservoir behavior. Existing workflows are also very much anchored towards modeling geology on a grid. So once we've defined the grid and its resolution, we have always a limit in terms of what the geology that we can represent spatially, the complexity of the geology that we can represent spatially. And if you want to refine the geology, if you want to refine the structures, that's difficult to do on these predefined grid resolutions. And more broadly speaking, the integration across different disciplines is always difficult because we have different software tools, different types of grids, different types of grid resolutions. So the idea of RRM, Rapid Reservoir Modeling, is that in a nutshell, we have developed a new open source software tool where we try to very rapidly create conceptual reservoir models. You also try to rapidly modify existing reservoir models as you get, for example, new data on board. You also rapidly, and so it's almost in real time, calculate some of the key static and dynamic reservoir properties. And the overarching aim is that we prototype reservoir concepts and models, and we test them with quantitative data using a very broad range of input data. So this could be seismic cross-sections, it could be outcrop analogs, it could be even a blank screen as we're testing different concepts, geological concepts. RRM uses a very simple, intuitive, interactive interface, and it's essentially to do things that are difficult to do using our conventional geomodeling tools. But it's not a replacement, it's not a plugin for, not a replacement for existing reservoir modeling workflow software package. It's not a plugin into existing packages or competitor. It's simply an additional step that helps you to make your life easier when you build reservoir models. The key components of RRM use the technology. We'll talk about each of these components in more detail in a moment. Use a technology called sketch-based interface and modeling, or SBIM, which enables this intuitive, easy workflows, and anyone can really use it. Doesn't matter if you're an undergraduate student or very experienced professional. You always start out from 2D sketches to build 3D surfaces. We sketch geology and cross-section map view because that's very familiar to geoscientists. And we then use these sketches to build 3D surfaces to represent geology, to represent structure, to represent the reservoir using these surfaces. We have a number of geological operators that ensure that any geological model is consistent, and we can build the models in any order and at any scales that allows us to allows our interpretations to evolve and sketch in any way that is most convenient to us rather means of sketching geological time or through some hierarchy of geological structures. Then we use flow diagnostic, which is not a new concept, and these flow diagnostics allow us to calculate some of the key volumetric and fluid properties as we're building the models in near real time. So sketch-based interface and modeling, and this is really the contribution that Mario and his team as computer scientists have brought to the project, is not a new technology. The key idea is in companies like Walt Disney, Electronic Arts, the car industry, the technical and medical science illustrators have used it for a long time. The key idea is that you sketch something in 2D and you have a computer algorithm that realizes the sketches that you're making and then uses these sketches to build a 3D model. So here, someone is sketching the outline of a heart, and then a computer algorithm builds from these sketches the 3D heart because there's just one shape or one type of how a heart looks like. You can augment existing sketches. For example, here we have a hand and we have some veins in the background of the hand. So you sketch these hands and you merge these two shapes. Or here there's a leaf and you can sketch the deformation of the leaf, and then that leaf is being deformed in a biologically consistent way. And we use that idea, or these ideas that have existed for over 20 years, or around 20 years, in the computer science, computer visualization domain for reservoir modeling. To do this, we use surface-based modeling, which is different from the existing sort of grid-based reservoir modeling. So all geological heterogeneity that we represent is modeled as one or more discrete rock volumes. They're bounded by surfaces. Call them geological domain. And that can work at any scale. So fundamentally, you could think of a geological domain being an individual grain and the pore space, or it could be the big para-sequences that you model at nearly the basin scale. Basically, any scale is possible to be modeled by surfaces. So the hierarchy of surfaces at multiple scales, faults, stratigraphy, facies, diagenetic bodies. And importantly, the petrophysical properties, they're always constant within a geological domain. So we don't do any geostatistics to represent geology. So this is exactly equivalent to a grid-based approach, but now the petrophysical properties are constant within a geological meaningful domain rather than a grid block of arbitrary shape. If you want to add more heterogeneity, where we draw another surface to define another geological domain. We have these geological operators that define how these surfaces interact with each other in a consistent way. So what does this mean? Here's an example of geological operators for existing surfaces. So we know that stratigraphic surfaces, they cannot cross and they cannot end within the domain. So Geology 101 tells us that these models A and B, they're geologically not possible. So assume we're sketching a model and we have these gray surfaces that represent some stratigraphy that exists. And then we have, in geologic time, we have a big erosion event, perhaps a fluvial channel eroding some of these surfaces. This new surface, this orange surface N that's being dashed, drawn here. And these surfaces, in a stratigraphically correct way, they can only interact in a certain number of ways. So if we find geological operators, for example, remove above, so if we sketch this new surface, then all existing surfaces above this new surface are being removed. So we could model an erosion event. We also the equivalent of remove below, so all older surfaces are being removed, or we only remove above or below the intersection of the new surface and all existing surfaces. So these are cases D and E. What this allows us, it gives us a lot of flexibility to sketch as we see rather than having to sketch in some geological orientation. So we can look at features first, the big features first. We can let or sketch in geological time or look at the most obvious things first and really have our interpretations evolve as we go along. How do you get from the 2D to 3D sketches? Well, we can interpolate. So you could have, for example, different seismic cross-sections and interpolate your sketches between those seismic cross-sections between your different interpretations. Or you sketch a cross-section and then in map view, you sketch the trajectory, for example, the direction of a fluvial channel, and that sketch then evolves geologically consistent along the trajectory of that path. Where you can have contour sketches in map view to sketch things like diagenetic bodies, salt domes, etc. And the software RM is very simple in terms of the graphical user interface. So there's some a number of buttons here that define which geological operators you use. You have a window where you sketch in cross-section map view, and you see the 3D model that's been built and the geological domains here. But there are no sub-menus, so it's really, really easy to use. And one of our sponsors said, I really like the software, but I don't like, my son has learned it much faster than I could. So it's easy for children to learn and play around with. How do we get from the static models to dynamic models? So everything in terms of geological models is done by surfaces. So there's no grid. The grid is entirely disposable. It's only generated on the fly when we need it for calculations. And because we have the surfaces always present in the background, we can then adapt our grid, refine it, make it coarser, finer to represent the geology at the scale we want to. We solve 3 equations, steady state equations, to provide visual and interactive information in nearly real time on the reservoir pressure time of flight, the reservoir partitioning, well allocation factors, and sweep efficiency, and also do flow-based upscaling for effective permeabilities. And essentially what we've done is we've implemented the seminal work that came out of SINTEF by Olaf Moyner, Knut Andreas Lee, and others into RM around the flow diagnostics on grids. And what this allows us to do is that as we're building geological models, as we're testing geological concepts, we get this really quick feedback on the dynamic behavior of the reservoir. So we can start selecting good models, geologically meaningful models that we want to use and study further full physics simulations using commercial simulators such as CMG. We simplify a lot of the physics here. So Eric talked about composition modeling. So then add the compositional modeling, the thermal modeling, black oil, etc., whatever we need to do to get the physical detail right once we've screened the initial geological heterogeneity and looked at different geological concepts. So here's an example case study. It's a classical case study. It's a shallow marine correlation from the Spring Canyon member in the Book Cliffs Formation, Utah, which is a classical outcrop where a lot of students, a lot of industry professionals go to learn about sequence stratigraphy. In terms of input data, we have 4 interpreted sedimentary logs, a wireline log, a map with the log locations. We know the average depositional strike and dip of the formations. So here we have loaded the logs, cross-section, then we simply start interpreting and testing different concepts based on the geological data that we have available. And here you see on the right-hand side, you see a number of the different geological concepts that we have created. And they're all based on different correlations and interpretations of the same geological data. As we're building these models, and it takes us minutes to build these models, we immediately get feedback on the volumetric properties of the different facies. So you see how the reservoir facies changes, the amount of reservoir facies changes, gross pore volume changes, and as we add and remove certain geological features based on our interpretations. And it's really not a complicated workflow. It's very simple to sketch these models and allow the different concepts to evolve and modify concepts. What you see here, so it's really interesting. You pass this RRM to users because they use it in very different ways based on their own experience and their own expertise when they interpret different correlations. Some use a top-down approach, others a bottom-up approach, others look at fluttering surface first, others interpret the obvious feature first. Some model create the models hierarchically. What you see here are, again, the same input data, the well logs, and the different geological interpretations of the same data, starting different. Every interpretation starts in some different way. That's again because we have these geological operators that allow us very flexible to sketch what we see and let our interpretations evolve as our understanding of the geological heterogeneity evolves. Here's now a 3D model that shows one of these correlations. What you see here is 3D model with the different geological domains, with the different reservoir facies, permeability distributions, pressure distributions, and the time of flight that tell us how is the reservoir, how are the different reservoir facies connected to each other, where would we see more effective sweep, less effective sweep, where do we see the biggest risk of breakthrough of the injected fluid phase, be it cold water in the geothermal reservoir, CO2 in a carbon capture and storage application, or water during the water flood. And it's always nice to show this in real time. So what you see is a real-time application of RRM that's captured in real time. So there's a top of a reservoir being sketched, little cross-section of a channel being sketched. Now on map, you will see the sketch of a channel trajectory. And then that channel is being immediately built in 3D. Immediately being created in 3D. We sketch the next channel and we use the appropriate geological rules to make sure to define how these two channels interact. Again, the outline of a channel and the second channel is being built in real time. We get a geologically consistent model of two interacting channels. I'm going to fast forward a bit if that works. Let me just change my pointer here. So now we're coming to the point where we have a model with little toy reservoir with the top and bottom surface, two interacting channels. And we now have these geological domains defined. We load our flow diagnostics calculation. So you see in this model, we always start with 4 wells, and one is injector, 2, 3 producer wells. We refine the grid because this coarse grid doesn't, this is again all in real time. We refine the grid, we move the wells around, we change the well completions. And as we're moving wells around, as we're changing the well completions, automatically the dynamic properties, the sweep efficiencies, time of flights are being updated. So now you see the time of flight distribution here, and from the injectors, from the producers, and you see how the time of flight evolves in the reservoir for this particular geological model, for this particular well configuration. We can move the wells around, we can change the geological model and redo the work. At the bottom, we always calculate recovery factors and dynamic Lorentz coefficients, well allocation factors. So we get this real-time feedback on the reservoir behavior as we are evolving our reservoir models and our understanding of the heterogeneity that's present in a reservoir. Everything we do is open source. So rapid reservoir modeling has a very clear goal. It's not to build very detailed multi-million grid block models for complex reservoirs. It's really to prototype reservoir models to get this quantitative feedback on flow behavior, for example, hydrocarbons, geothermal, CO2 storage, even groundwater flow systems, as we're evolving our understanding of the geological heterogeneity in the subsurface, as we're testing different geological interpretations on the same reservoir data. The potential user base is much larger than industry professionals. So where we see, coming from the academic side, is really for geoscience students to discover 3D relationships. So RRM works on surface-based PCs. So when we can travel again, we can take students out to the field. We're all itching to go to give our students RRM on this surface books. So on field trips, they can stand in front of the outcrop, they can sketch models in 2D, create these 3D models of the outcrop, and understand how geological heterogeneity they see in an outcrop impacts fluid flow, and how changes in heterogeneity, changes in reservoir connectivity, impact flow behaviors. I think it's a wonderful teaching tool. It's a really good tool also to communicate in across disciplines between geology, between engineering, and decrease the turnaround times when we try to communicate how geological heterogeneity impacts fluid flow, because we don't have to build a complex 3D Petrel model first, or whatever model first, and then load it up in a really advanced reservoir simulator. Both Petrel modeling and reservoir simulation have their fundamental use. They're not replacing them. What RRM allows us to really make both communicate much faster. If you're interested in trying it, please do so. So there's a link here at the bottom from where you can download the source code for RRM, because as I said, it's all open source. So to conclude, what RRM is, it's a prototyping tool for 3D geological modeling. We think a really intuitive, really easy to learn sketch-based interface. We do have a manual, but most people don't read the manual because it's simple to use. What you see here on the right-hand side is the work that a master student has done in 7 weeks the summer to model geological heterogeneity in a carbonate reservoir platform. And when some of you may remember the presentation I think I gave last year on the open access carbonate reservoir model, PhD student who co-supervised this project said, well, if I would have had RRM at the beginning of my PhD, I could probably done my PhD in 2 years rather than 4 years, because a lot of the things I try to do with conventional workflows are so difficult to do, and RRM is just making things much easier. Try to challenge everyone to build a model like you see it here. Sorry, where's my mouse? Like you see it here in the center, model like this in a conventional reservoir modeling workflow. What I forgot to mention also, RRM has an interface to the conventional reservoir simulation, reservoir modeling packages, so you can then load it up in your favorite reservoir modeling software, in your favorite reservoir simulation, to do all the detailed dynamic simulations afterwards. So RRM really is for prototyping 3D geological models, to do things that are difficult to do in existing surface packages. There's existing modeling packages. It's very intuitive interface. These geological operators are key because they give us the flexibility to sketch in any order at any scale. We apply those operators on the fly, and we always get this real-time feedback, near real-time feedback on quantitative measures such as facies proportions, facies volumes, reservoir volumes, and with the flow diagnostics, is real-time feedback on some of the key dynamic and quantitative properties of the reservoir. And using that knowledge, then can select models that we want to study in much more detail using the more conventional reservoir modeling and reservoir simulation workflows. It's not to take anything away from CMG or from any other reservoir modeling software packages, simply to help these two domains to communicate more effectively and make our lives much easier. And with that, I'm very happy to take any questions. Thank you for your attention.
Thank you, Dr. Geiger. We have about 3 minutes for questions, but let me summarize 2 questions, which are similar from Gaurav Sharma and Dr. Iraj Ershagi. Basically, they're asking how would the role of phases modeling and diagenesis, as well as maybe variogram, the traditional geomodeling type, be conditioning within this representation.
So we don't do any, so this is really important. We don't do any geostatistics in our reservoir models. I'm just going to skip back to the right slide here. The slide here to the right. So every every bit of geological heterogeneity we model explicitly. So we know from the huge wealth of outcrop analog data, for example, how certain geological features between wells could be distributed, crossbeds, etc. So rather than trying to model these geological features by geostatistics, we would sketch them, and we have actually ways to save them as templates. So you have to sketch them only once, and then you can just copy and paste them. So we use our geometric understanding of reservoir heterogeneity to model geology, rather than trying to represent it by geostatistics. How do we condition this? Well, we condition this with the appropriate geological analog data and the understanding that geologists have of how certain sedimentary features look in 3D. Now, if you want to do geostatistics later on, there's nothing that keeps you from overprinting geological structures that we have modeled with geostatistics, but in your favorite reservoir modeling software. But that's not the key that's not the primary driver for RM.
Okay. Another question from Saeed Mohandam. Is structured discretization available in this algorithm? Is it possible to use this fluid mesh configuration in solid mechanics simulations? For solid mechanics stress simulations, we surely need unstructured high-order elements.
So that's a really good question. So we've played around quite a bit with unstructured grids because for that reason that we thought an unstructured grid allows us to represent geology even with even more detail. And if you want to do geomechanics, it's much nicer to do on, say, tetrahedral finite elements. But what we learned quite painfully is that as the geological models, I'm going to forward again here, so become really complex to the level of detail that you see here on the right-hand slide. We have thin pinched out zones, and we capture the geological detail in our models. Unstructured grids, the various meshing algorithms we've tried to use, they sort of died halfway through, and it doesn't help you if you can create a model in complex model like this in half an hour, and then it takes you, multiple tries to mesh it. That's why we went back to this really simple structured grid. You can refine it on the fly. It's always stable. It's always very fast. Hopefully next year we're going to start looking at geomechanics, and then we need to go back to the drawing boards and how we use the existing meshes in an effective way if you want to do some geomechanical simulations. At the moment, it's simply not possible.
Okay, thank you very much for the talk.